All right, our lesson tonight, which is going to be the next part of the application of Newton's laws module, is tension and spring forces. So tension basically would be strings and ropes and are represented in a free body diagram as a tension, which is abbreviated as the letter T. They are treated as any other force, and there can be more than one tension acting on an object in a Newton's law problem. Also, springs is a force of a spring on an object depends on how much it is compressed or expanded. And this is something called Hooke's law. And the force always points in the opposite direction that it has been expanded or compressed. So we're going to jump right into some examples when it comes to tensions. So let's read here. It says that a 10 kilogram block, which is what's represented here. Oh, I want to change my color. Sorry. A 10 kilogram block, which is represented by that green ball in the free body diagram, weighs or is hung from two wires. The wire on the right makes an angle of 35 to the horizontal, so that would be right here, and applies a force of 55 newtons. There's a wire on the left also at an angle, and it's asking you to draw the free body diagram for the forces of the box. So if we weren't seeing that, we would draw the same thing. We have a box, we have one that we know the angle is going to the right, and then we have another one, which we don't know the angle, and then we also have the weight pulling it down. So we can call this tension 1 and tension 2. So the question states, what is the weight of the box? So the first thing we got to do is determine, and that's easy by finding weight equals mass times the gravity. So 10 kilograms times 9.8, and so we're going to get 98.0 newtons. And it says, what is the equation on the x-axis? Remember to break forces at angles into the components. So we have tension 1 minus tension 2 equals 0 because this box is not being swinging, so it's at rest, so that's why we know it's 0. Or another one is tension 1 cosine theta minus tension 2 cosine theta 2, which is also going to equal 0 because, again, the object's at rest. So the next question says, what is the equation in the x-axis? Remember to break the forces at an angle into components. I'm sorry. I just wanted to bring that onto this slide. So that's what we just did on the previous slide. The first question says, what is the equation in the y-axis? So again, it's not moving, and we know that the weight is pulling down and the two tensions are pulling it up. So we obviously know that the addition or the sum of the two tension forces minus the weight is going to equal 0 because, again, this object is at rest. Or since we have the components, we know that sine can be used to find those vertical components, which is in the y-axis, minus mass times gravity or weight, and it's going to equal 0. So basically we're just interchanging those variables like we've always done. This question says, what is the x component of T2? So we're going to find the x component of that second tension. So we know that 55, which is the force right here, and we have cosine 35 because the angle is given to us in the problem, and we're going to get 45.1 newtons. So now it's asking what is the y component of T2. We're going to plug in what we know from the formula that we have formulated over here. We're going to have or add in 10, which is the weight, 10 kilograms, times gravity 9.8 minus 55, which is the force, sine 35, and we're going to get 66.5 newtons. Should have it in here. Alright, so what is the magnitude of the unknown tension? So the problem, it didn't give us a force. So we know that the equation can be rewritten up here by finding the square root of the x component and the y component. So if we plug in those numbers that we just calculated in the previous slide, square them, find the sum of it, and then the square root of that, your unknown tension should be 80.4 newtons. Now it's asking what is the direction of the tension of the unknown one. So now we can have the inverse tan function from the previous module that we were talking about when we're finding vectors. The tension in the y divided by the tension in the x. So we have 66.5 and 45.1, which is what we found out. So we should find the inverse of dividing those two numbers, and we should get 55.9 degrees. We know it's clockwise from the negative x-axis, which is important to understand. Alright, now that was the example for the tension. Now we're going to move on to springs. Here is the equation for springs. We have a force, which the springs it has a sub s equals negative kx. So remember that the value of s is never negative, and the negative sign in the equation indicates that the direction is always opposite to the expansion or compression of the spring. K is the spring constant and is specific to the spring being used, and x is the amount of expansion or compression in meters. So remember, x is going to be a distance recorded in meters. Alright, so a block with a mass of 10 kilograms is being pulled to the right by a string. The block accelerates at 1.50 meters per second squared, and the spring constant of the spring is 25.0 newtons divided by meters. The surface has a coefficient of friction of 0.450. It says draw the free body diagram. So we have the box that's right here. We know that a weight is pulling it down. We know the normal force is going opposite in the direction of the weight. We have the force of the spring, and then we have also a coefficient of friction, which is pulling it in the opposite direction. So it says write an equation for the x-axis. So looking at a free body diagram, we have the force of the spring minus the friction, which is going to be in the opposite direction, equals mass times acceleration. Write the equation for the y-axis. So we know that the object's not moving up or down, so that means it's going to have the normal minus weight is going to equal 0. The next question says calculate the value of the normal. So we plug in what we know into the formula equation. We have 10 kilograms multiplied by gravity, 9.8, so we're going to have that force of 98.0 newtons, and then also we're going to calculate the force of friction. So it's given us that coefficient in the problem. We have the force of 98, which we just calculated over here, and so the force of friction is going to be 44.1 newtons. So again, if you remember the free body diagram, that's what we just calculated in this direction. So now it's saying calculate the value of the spring force, so we need to go to the right direction. So we have the formula that we wrote in the beginning of the problem. We plug in what we know, so we have 10, again the mass, 1.5, which is the acceleration, and then we're going to plus that 44.1, and we're going to get 59.1 newtons. Now we're going to calculate how much the spring has been expanded by to apply this force. So this is where we're going to use our new formula. We have the force of the spring, which is what we just calculated, 59.1, and we're going to divide that by 25 because that is the spring constant, which is given to us in the problem up here. If I could find it. Oops, everything just went away. And down here, after you plug in those numbers, you should get 2.36. Oops. No. I think I accidentally jumped out. Oh no, it's the end. So that is it for our lesson on tension and springs.